So, here we are starting the holy grail of finance, the Black Scholes formula for pricing a European call option in continuous time. That paper was published in Journal of Political Economy, actually they could not publish it elsewhere. The Ito's calculus approach that we have used here is largely due to Merton, Robert Merton of MIT, who is a student of Samuelson. So, it is also called the Black Scholes Merton formula. Okay. So, Black was a mathematician and did his masters in mathematics and PhD in physics actually, and Fisher Black was possibly one of the greatest geniuses or possibly the only genius finance has ever seen. And nowadays, to honor people in finance, there is a prize called the Fisher Black Award, and its first recipient was Professor Raghuram Rajan. So, again we go back to the pricing formula. It is exactly like European call option, is exactly everything is same. Only I do not say it is up and down. I do not say this price will go up or price will go down. Price will take some value at a given time t. The price will take some value st. So, the price process, it just describes a continuous time stochastic process. It does not tell me anything else. That is now the difference. Now, once that is done, how do I know? So, I can still have an option, which a call option, and I agree at time t equal to 0, I make a contract to sell a share of a stock at the price k, which is the strike price. Here obviously, this is between the upper price and the lower price that we saw in the binomial case is not valid. That sort of statement cannot be done here, because you do not know what is ST. So, at time capital T, the worth of the option is done in the same way. So, at time capital T, the worth of the option at time capital T, you have to see whether the price is bigger or smaller than k, and then you exercise the option or you do not exercise the option, fine. Now, what would you do? As before, you will charge a price for the option, which would be the Black Scholes price at time t equal to 0, and then you will use that money in the money market, in the market by trading, keeping some part of the money in the money market, use some part of the money to buy some shares of that given stock. See, again I reiterate, we are operating in a one stock market, which consists of one stock and the money market. It does not consist of anything else. It is a very, very idealized situation where you expect complete hedging, complete safeguarding of your risk, but this is not truly the scenario in the market, which we do not have time to study. It means a separate course if you want to study in incomplete markets. Okay. So, what I want to do is now, in a continuous time setup, if I start with x0 amount of money, then at every time, here there is no time period, in a continuous time, how would I actually go on building up my portfolio? So, my portfolio would now vary continuously as a continuous function. So, how will I do it? So, at time t, So, what happens? I have written this portfolio, what things this calculation we have done in the last part, but here we are doing it in a very simple way. So, at time t, the worth of my portfolio, that is, here I am looking at the change of my portfolio value on a very small interval of time, and I am assuming that over that small interval of time I am holding the delta t number of shares of the stock. This is so small that I am assuming that okay, they are almost side by side. Of course, there cannot be side by side in a continuous time framework, that is just absurd talk, but it is so small that I can means I cannot trade immediately. Nobody can ever trade buy now, sell now that same instant. It is not possible, because in a continuous time set of given t, there is no next time, there is no time t which is just next to t. So, there is always a very small gap. So, you are holding, and because the gap is so small that we say that okay, the whole process is continuous in a from a theoretical point of view. That is why the binomial process is very handy when you are actually doing the game, doing the real computations. So, now what do? You hold it over that very small time period where on which the price changes by this amount, and during this time with your interest rate RT, you had held. So, what is your interest rate? Now, interest you are given, you had xt amount of money at time t, and you bought delta t shares with the price st. So, the remaining money you put in the money market, and you are holding it for a very small amount of time dt, right. So, it is RT into dt. So, for all that small period, that fraction of a period, so you do not charge, as we have discussed about interest rates earlier, you do not charge the interest rate over the whole some big period, you just charge the interest rate over that fraction of time, assuming that on that fraction of time or over a slightly larger interval than that, the interest rate actually is almost same. So, this is the portfolio wealth equation. Portfolio wealth. So, it is a portfolio wealth equation. Okay. So, I write down the formula. This is what you already know. When it comes to actual Black Scholes pricing, all these would be constant, it will be much simpler. So, do not bother about it now, plus the same part. Okay. Now, once that is done, you can now write this as, so club the dt term, club the dwt term. So, here you multiply R t delta t S t dt. So, that you can pick up with delta t alpha t S t. So, an R t x t dt is separate. Okay. Plus what you have here, this into this delta t sigma t S t dw t. Now, if you look at that, I can write this term in terms of sigma t theta w t, right. So, I can write this thing as R t, because I can write this term in terms of the theta from the formula which we have, plus delta t. So, this will become sigma t into theta t, this alpha t minus R t term, just by the definition. So, this means now here I will get delta t sigma t S t into theta t dt plus dw t. You see, I have now expressed the wealth equation also in terms of the risk neutral measure, and that is the fundamental thing. So, what I have got here is dxt R t x t dt plus delta t sigma t S t dw t. This is what I have got. Finally, this is what I have got. So, I have expressed the wealth equation, the wealth process in terms of the risk neutral measure. Now, what about the discounted wealth process? So, everything is very important that we have to look at wealth process, we have to look at the discounted wealth process, and the discounted wealth process is a martingale. That is what we really have to show, what we have done in the previous lecture in the previous week. So, once we show that the discounted wealth process is a martingale, then we are on track. So, let me rub this part off and look at what is the discounted wealth process. Now, if I write dt x t, so now I will write the discounted wealth process, the differential of the discounted wealth process. Again, I will go by the Ito's product rule. If I use Ito's product rule, it will simply come out to be delta t. I am just writing the result because I do not have so much time to dTst. So, if you remember, this is exactly what we had in the discrete case. The wealth process is nothing but the amount of shares into the discounted stock price. This is exactly what we had, just remember that result. So, this is exactly what we have. Now, what is this? We know that this is nothing but sigma t S t dt and so it simply means x0 is x0. So, it is dt is d0, which simply means d0 is 1. So, xt is x0 plus 0 to t delta t sigma t dt dw t. So, what we have proved, because Ito integral is a martingale, so we have proved again that the discounted wealth price dtxt is a martingale under the risk neutral measure P tilde. तो साफ कर दीजिए, कट. Our next goal is to show how do we price in a continuous time setup under risk neutral measure. So, pricing under risk neutral measure is now what we are going to study. So, what happens that when you look at the worth of the option at time t, capital T, the terminal time, when you are supposed to exercise the option, it is this simple fact. Of course, if you change the strike price, this will be a function of t, right? It is a random variable. So, if you change the time limit, we can vary that t, capital T. So, it will essentially be a non-smooth function, right? It will be 0 and then it will be up. There will be convexity of Vt, okay, we will not get into all those things. So I am little excited about convexity. So, what are the things that we are now looking for? Because Vt will depend on all the information till time capital T. So, Vt is a Ft, which is F, measurable random variable. Now, by the fact that it is a complete market and we do complete hedging, so we need that my final wealth process xt must be equal to Vt almost surely. See, all these equations, when you write equations between random variables in probability theory, all these equations, whatever we are writing in finance, all these equations are in almost surely sense. There is no other sense basically, right. Essentially what it means that in between this time interval 0 to t, at any time you can want to buy the option. Suppose you buy it at some time t naught, then t naught minus t is your time to expiration. Your time to expiration of the option is less. But here, what would be the price that I should ask for you if you come to me at time t naught and not time 0? Then the price that I should be asking you is v t naught. But what should be v t naught? V of t naught, just like we have done in the discrete case, should be same as my portfolio value. That is the whole idea. My portfolio value is equal to the worth of the option. That's exactly the principle, and there is nothing about it. Now, so if you choose initial capital Vt is V0, that is x0. So x0 is your initial capital, V0 is the price. Actually, the Black Scholes price tells you at any time what should be the price, starting price. The price will change if you, so I announce that I am selling this option. The option contract is announced at time t equal to 0 and will expire at time t equal to capital T. You may come any time and buy in between, but then the price will depend on the choice T. Now, what happens is that how do I now actually price it? Look at the interesting thing. We know that the process dtxt, the discounted wealth process, is a martingale under the risk neutral probability. So, dt xt is the conditional expectation of dt xt given ft. But by what we have discussed, if you want a complete perfect hedging, and because the market is complete, we have a perfect hedging dt vt given ft. Now, I can now write this equation as xt is equal to 1 by dt E tilde dt vt ft. Now, you understand that at time t everything is known about dt. So, basically if you can take whatever is known out of the expectation sign, you can bring the thing inside also. So, this simply means xt is equal to d of capital T by d of small t. So, it is exponential d of capital T by d of small t Vt Ft. But then we have also said that every such any point that you take between capital 0 and capital T, xt must be equal to Vt, the price must be equal to the worth of my replicating portfolio. So, Vt must be equal to E tilde dt by dt Vt. So, let me write it down more fairly here. So, my option price under risk neutral pricing is Vt is e to the power minus small t to capital T r to the power s ds Vt given Ft. So, this is the risk neutral pricing formula. Of course, t is between 0 to t, that I do not have to tell you every time, I am telling it t is between 0 to t, just do not forget that. So, this is the risk neutral pricing formula. And this would be used to actually figure out the Black Scholes price. Okay. So, now we will start the Black Scholes formula. In this case, dst is fixed, means if you write it under the risk neutral measure, it will be where R is RT is equal to R, it is fixed, plus, see what happens when you are changing from a standard measure to risk neutral measure, from market probability to risk neutral probability, you change the drift, you change the rate of return, but you do not change the volatility. That is the key idea to keep in mind. That is not what volatility is assumed to be constant here. If you take risk neutral pricing here, I am just talking about risk neutral pricing. So, this would be the behavior. So, R is constant, sigma is constant. So, R sigma, if you want that alpha also, if you just take in terms of dWt. So, if you write in terms of dWt, dst is alpha st dt plus sigma st dWt. So, and alpha, these are all constants in the Black Scholes pricing, all constant. So, then your dt, d of capital T is nothing but e to the power minus r small t. So, because of this your dt now let us look step by step at the pricing formula that we are going to do for the Black Scholes pricing formula. Let us also remember the Black Scholes pricing formula at Vt, it just not only depends on T, it essentially, though we write Vt where value at worth at time T, it depends on the C, this is a cost which depends on not only T, but the price of the stock at that particular time, right. So, that is how strike price would be actually fixed basically, and the value, the worth would be, sorry, not strike price, I am making a mistake, because based on this Vt would be fixed. The Vt needs a dependence on this. Right. Now, but we are computing this with risk neutral measure, and I write E tilde e to the power minus r capital T minus small t, where we are in terms of the integral Vt, V of capital T. So, V of capital T here is max of St minus k and 0 given f of t. Sorry. So, this is my formula. Now, if I go by this formula, then I know that my S of t, if I go by this formula in the risk neutral pricing, right, where your R is of course the standard fixed interest rate, St is S0 into exponential sigma Wt, because this is the constant, so integral 0 to t dWt is Wt, because W0 is 0, plus R minus half sigma square dt. This is the formula. Now, what about S of t? So, we call this formula as star, and then S of t naturally is the terminal time. Here it is any time and here is the terminal time, exponential sigma capital T plus R minus half sigma square T. Now, if I divide this line, if I call this star, double star. So, dividing double star by St, dividing this expression by dividing the St, dividing right, basically nothing, you are writing now you have to express St in terms of small st. So, divide this side by St, so divide both sides of star by St, and then use divide both sides of double star by St and use star to get S of capital T is S of small t, because S0 will cancel, exponential sigma W tilde capital T minus W tilde small t, sorry, it is not dt, it is t. Here it is t, not dt, it is the integral 0 to t dt is t. So, plus r minus half sigma square capital T minus small t, that is what you will have. So, here also there is a change, right. So, here this will be capital T, this will be small t. Now, what would be the interesting case is, now let us write capital T minus t, it is the time to expiry of the option. So, that let us put it as tau. Let tau be is equal to capital T minus small t. Once I do that, then let us see what my expression becomes. Okay. And let me put y as w tilde capital T minus w t by root over t minus t, that is root over tau. Let me put this variable. Now, first we have to decide w tilde t is a normal random variable with mean 0 and standard deviation variance t. This is, so w t minus w t, sorry, w tilde t, this difference is a normal random variable. So, w tilde t minus w tilde t is a normal random variable. So, I made this change, is a normal random variable with mean 0 and variance t minus t. So, standard deviation is root t minus t, which is tau. That is from the basic fact about, because t is strictly bigger than t and because of the independence of the non overlapping intervals. So, and this comes from the very basic definition of the Brownian motion, that this difference would be satisfying this. We have to then go back too much details into Brownian motion, which is in the first part. So, kindly have a look at the first part. So, this is what you will have. Once you have this, so y, so you take a normal random variable and scale it. So, you will get a random variable. So, y would be a normal random variable with mean 0, but the variance is root over t minus, with the variance is 1, because here if you take the variance of this thing, it will be, so if you take variance of y, so mean would be 0, if you take variance of y, then it will become 1 by tau times variance of w tilde t minus w tilde t, just by the basic formula variance, because these are independent random variables w t minus t. So, these are independent random variables, right. So, there is no other variable. So, it is just one variable. So, this is just one variable, right, w tilde t minus w t. So, it is 1 by tau variance of this. Variance of this is of course tau t minus t. So, it is 1. So, y is now a standard normal variable, right. So, this expression has to be kept in mind. Okay. So, which means we can now write down ST so ST can be written as S of small t into exponential sigma, this one, sigma root tau y plus r minus half sigma square tau. This is the expression. Now, observe that this expression is independent of f t, because this is looking at everything beyond the time t. So, this expression is independent of f t. Okay. So, this is a very, very important fact, because when we do the risk neutral pricing formula, which I again write here, which is CTX, which is CTST equal to exponential e to the power minus r capital T minus T max of ST minus K and 0 FT. See, I am computing the ST because I have to put it here. That's the game. That is why I am writing this. So, keep this ST. Now, I will rub this part and do the further calculations. So, you have to understand that this part, this expression is independent of FT, because here everything is in terms of tau, which is beyond small t. Now, what we are going to do, we will treat the random variable ST as if it has some value x. The way you compute things, you write density functions etc. in probability. So, let us just do that, and let me write it down. CTX is equal to exponential e to the power minus r tau, which is T minus capital T minus small t. So, max of x of exponential let me make a, I think there was a small correction I want to make. Y was minus, because there will be some sign problem, t by root tau. So, here there would be a minus sign. So, in the previous expression of S of capital T, so just check this expression, S of capital T is ST into exponential minus sigma root tau y plus r minus half sigma square tau. That would be the expression. So, this minus is been taken by Shreve because there will be some sign issues, but this is not a very big thing. You can take it in the same way which I had taken. The sign issue can be handled at the end, but some books take it like that and some books, so just take the minus sign. So, we will take the minus and go with Shreve, because I have already announced that I am doing things from this book. Root tau y plus r minus half sigma square t, this ST minus K 0 max of this slash FT. So, I can write this as CTX using the fact that y. So, here my random variable is y. So, this is a function of y. So, I am just writing down the expression. So, 1 by root 2 pi, I am assuming that you know very basic facts about statistical distribution, especially the normal distribution, the most important one, E or tau max of x into exponential minus sigma root tau y plus, now we should not put root tau y here, this has to be root tau y minus plus r minus half sigma square tau, sorry, this is tau, sigma square tau. See, it is only the complication of the expression that makes the whole thing look so damn bad. Max of this in e to the power minus half y square. So, 1 by root 2 pi we have taken out. So, basically you have to find, so this expression is meaningful when this is greater than or equal to 0, otherwise it is 0. So, to find when is this expression greater than or equal to 0, right. So, this expression we have to find whether this expression is greater than or equal to 0. So, if this expression is greater than or equal to 0, when x into exponential of minus sigma root tau. So, the sign issues come here actually in this, it does not matter. So, it just is a matter of convenience, that is all. R minus half sigma square tau, this should be greater than k, sorry k. So, I can take x, assuming that x is non-zero, of course positive for the time being. Okay, I can also bring this here, x of k is greater than equal to, so e to the power minus sigma root tau y plus r minus half sigma square tau. So, you put the minus here, so it will become minus. So, you now take log of both sides. So, this would imply that log of x by k is greater than equal to sigma root tau y minus r minus half sigma square tau. So, you take log is the increasing function. So, you take the exponential element is taken off by the log, log is log to base e. So, this implies y is less than 1 by sigma root tau log of x by k plus r minus half sigma square tau. So, I will call this expression, this whole expression as d minus tau x, as Shreve writes, we will call this expression sigma root tau. So, sigma root tau comes here in the denominator from here. Of course, t cannot be equal to t, then it has no meaning, because we are pricing it at some t which is strictly bigger, strictly less than t. If there is 0, when t is t, then there is no meaning, then it will be 0, then it is a very, then it will be a different calculation. So, here, so this is this expression log x by k plus r minus half sigma square tau. So, this is the expression. Now, once this is done, we will go to our next step. So, basically then my integration has to be that y has to be less than this. So, my integration, so when once y is between minus infinity to this number, this is greater than equal to 0, right. If y is strictly bigger than this number, then this is less than equal to strictly less than 0, and this whole thing becomes 0, the max of whole thing becomes 0. So, now what you will do is that we just have to integrate, find the integral from minus infinity to that, and that is exactly what we are going to do now. So, I will be slightly faster. So, I am just writing down everything in the way it was. So, here I can make this. So, now I can take the minus this into this and separate the term with the k and separate the others. D minus tau x exponential. So, I am pulling in this inside minus y square by 2, which is this been pulled inside, and odd tau e odd tau gets cancelled, e odd tau minus e odd tau. So, e to the power 0 is 1. So, that is what happens, minus sigma root tau y plus minus sigma square tau by 2. This is one thing into dy minus 1 by root 2 pi. So, here in contrast, see, we had also spoken about Black Scholes things in the part 1 at the very end, but there we wrote down the differential equations whose solution would give me the Black Scholes price. But here we are going to explicitly calculate the solution without recourse to differential equation, but just by here it is a minus sign, it is not equal to this whole thing minus this. So, I am separating the k part also, e r tau k into e to the power this one, e to the power minus half y square dy. Now, this thing can be taken out because this does not depend on y. So, here you will have, if you do some little calculations, so you will have x by root 2 pi infinity to d infinity tau x, and it can be written exponential of minus half y plus sigma root tau whole square, this whole thing dy minus e to the power minus r tau k into minus infinity to d. So, that of this 1 by root 2 pi minus infinity to d. So, it is a distribution function, cumulative distribution function of the normal distribution, which we write as, which is standard as, it is standard all over the world to write this as phi of tau x. So, probability at y is less than equal to d minus tau x. So, here also you can put z equal to y plus tau sigma root tau, then dy equal to dz, and then you put here this plus sigma root tau in this limit, and so this equation would become x root tau minus infinity to d tau x plus sigma root tau into e to the power minus half x square, or sorry, z square by e to the power half z square dz minus e to the power minus r tau k phi of d minus tau x. So, this thing suppose I write that d minus of, so d plus of tau x is equal to d minus of x tau, sorry, tau x plus sigma root tau, and that would give me, if you do that, if you do the simple calculation, that would give me 1 by sigma root tau log of, same thing, only the minus changes to plus, log of x tau k plus, here there was a minus, here it will become plus, r minus half sigma squared tau. I think it's just a plus minus adjustment. So, what I can write here, if I write it in this sense way, then I can write finally Ctx. So, this is nothing again but the distribution function of the standard normal distribution, x is of course outside, x of phi of d plus tau x minus e to the power r tau t minus t k phi d minus tau x. So, maybe, so this is exactly the Black Scholes formula, and we are at the end of the course, and so let me now write down the Black Scholes formula in all its glory that you want. So, the price, the Black Scholes price or Black Scholes Merton price at time t, which is Vt, which is nothing but C of TST, is equal to ST, x is now replaced by ST, x was playing the role of ST, phi of d plus t minus t ST minus e to the power minus r capital T minus t k into phi of d minus t minus t st. So, you just rewriting this. So, this is exactly what we required. This is our Black Scholes formula which we have computed. Of course, you have to use the standard normal tables, that does not mind. So, here we have essentially finished the course. So, in the next class, which is the last class, which is possibly mandatory to take, we will basically sum up what we have done, and maybe I will give a hint to find the delta t. Of course, you can ask me that if I am really the guy who is doing things in the continuous time, the guy who has sold option, what is this? Thank you very much for attending this 10-hour long course in finance. We will have a bye-bye class in the next one and finish the course. Thank you.